Hello everyone, most welcome to this session about solid-state battery research and the promising future about this research, and hopefully also industrialization and benefits for Europe. And today we have a quite interesting program, if I may say it myself, with a short lecture by University of Gießen about solid-state batteries, a future outlook. And that is followed by one panel discussion more on sort of research highlights with the title, How to Accelerate the Research to Enable Solid-State Batteries. And we have collected some very experienced people in this field. And you are also welcome to give some Q&A and write your questions in the chat so that we can post them to both the panel and of course to Jürgen for his lecture. The second panel discussion is about how to enable a solid-state battery market. And here we have also experienced persons from industry and different sectors of industry. Some might even be in production and have sales already when it comes to solid-state battery applications. And then we have a general Q&A, and we close this after 1.5 hours. So welcome to this session, and I hope it really will be interesting discussions. And the reason why we have chosen this sort of topic of how to accelerate the research to enable this, both the market and to the research as such, that is because in the Battery 2030 Plus roadmap, we are working on tools that could fit many different of the future chemistries. And by being chemistry agnostics, we realize that we still have to think about the chemistries, how we can sort of develop these tools and take advantage of the digitalization coming up, but also the situation of the battery value chain where we need also to think about raw materials and really making the best use of the energy storage solutions we have with batteries. So with this, I welcome you again, and I also welcome Professor Jürgen Janek, University of Gießen, and I'm very, very proud that you are here. And maybe I should have also said that I'm Kristina Edström, I'm Professor of Chemistry at Uppsala University, and will be the moderator. I forgot about that, sorry. But now we have the full attention on Professor Jürgen Janek, and congratulations. You are kicking off a big solid-state battery project in Germany today. And we are very, very interested in hearing what you are doing and your perspectives on the challenges we see for solid-state batteries. So please.
Well, thank you. Is my mic, can you hear me,
We hear you well.
Very well. Yeah, thank you, Christina, and also all the other organizers for inviting me. It's in fact a great pleasure to be here. And as I was originally asked just to provide 5 slides to support my, let's say, thesis, I really try to be brief, and this will be rather, I would say, an attempt to provide some thesis and maybe some provocative questions and ideas for the upcoming discussion of the panel. So I called my brief presentation On the Route to Solid-State Batteries because we are obviously not there, otherwise we would have them, and otherwise we would have gigafactories producing solid-state batteries. So I think most of you will be aware that we are in a kind of hype situation. To make the situation as simple as possible, I would say we are in the age of lithium-ion batteries. We create gigafactories and already have some gigafactories on lithium-ion batteries, and most of you will know how they look like. And many of the, let's say, early contenders of the lithium-ion batteries, like the metal air batteries or the lithium-sulfur batteries, at least when it comes to their use in electric vehicles, would say have fallen down and are considered at least not being real contenders for the lithium-ion battery yet. or anymore. And the question is, the solid-state battery seems to be one of the potential, let's say, not only contenders, but maybe one of the natural evolutionary developments out of current lithium-ion batteries. So let's look a bit into that. Next slide, please. So I structured my brief presentation into a one slide on just looking to the status quo and benchmarking, which is always important to really know how far are we really and where are we with the development of a certain subject. Now, and then I will briefly summarize some key challenges, and from challenges, of course, we come to key tasks. And as Christina has said, I will then, of course, also have just one slide on what we do here. And if I say here, we mean just in Germany. Of course, we all have also our international partners, but this is something which is funded by our federal ministry, and we'll tell a bit about that. Next slide, please. So let's come to an important point and that is the benchmarking. Now, this busy graph, I think, needs a bit of time to explain it carefully. So what you see, if you're familiar with batteries, is a typical Ragone chart. Let's concentrate first on the left graph, where you see in the top right region, the kind of target region, which is the lithium-ion battery and the lithium-ion battery cell, where we have, of course, specific energies that already go, I would say, into the direction of 300 watt-hours per kilogram. We have high specific power, and I would say a standard 18650 cell, probably not really of the top state of the art, is already, of course, up here. So this is, I would say, the performance of a conventional lithium-ion battery, and you know this is graphite anode, this is a typical organic electrolyte, and mostly a layered oxide compound like lithium, like the derivatives of lithium cobalt oxides, or lithium nickel cobalt manganese, or lithium nickel cobalt aluminum oxides, briefly abbreviated as NCM or NCA materials. Okay, so these are full sets. Now, what you see here then in these data points is all the data that we were able to collect last year, and we published this paper, and we put together all data we could get that were available, publicly available, as full data sets. So we excluded data where we only had, let's say, just an energy density or whatever, so only a few numbers, without being able to fully rationalize all the data. And then you will see, well, the amount of data is not, well, it's not too much. In fact, these light blue curves up there are data by Toyota for high energy and power cells. The red dots are own cells, which are not really optimized. But these data are all for solid state cells with inorganic electrolytes. I have to emphasize that. So this is for room temperature operation, 20 to 30 degrees C, room temperature operation of lithium systems. But these data are only on materials basis, without housing. So it looks as if it's not so far away, but in fact, there is still some way to go. And this is, I think, one of the early conclusions. There is still some way to go for solid-state systems really to meet the performance of solid-state batteries. And this graph, of course, does not include information on cycle stability, which also, I think, is excellent for lithium-ion batteries and still has to be improved for solid-state systems. Now, at the right side, you see data for elevated temperatures, 50 to 100 degrees C, which is, I think, quite, well, which of course means that we move into the polymer region, where the PEO-based lithium metal polymer batteries are in fact approaching relatively good performance. But what you see up here is data by Samsung for a ceramic electrolyte that was also heated to 70 degrees C, which seems already to approach quite reasonable performance. So at elevated temperatures, I think the picture looks a bit better. But of course, I think for the individual small electric vehicles, I think nobody expects that heated batteries will be a solution. So this is definitely a solution for, I would say, something like buses who have really regular routes where heating in a well-planned daily plan of driving schedules is a reasonable part. or let's say reasonable thing, because these devices or the vehicles really go more or less all day long. So there it's a solution, but it's definitely not a solution for the individual, let's say small scale mobility. So that means there is still some way to go. And honestly, I think I'm always a bit surprised about so many, I would say, very, very positive claims saying that we will see solid-state batteries already in a very short period as a mass market product. I think there is still some way to go. There is always very positive reports by serious players, like Toyota, for example, who have their demonstration cars, and like some companies who are really transparently reporting their data. But by and large, I'm always a bit afraid that we're in a period of exaggeration and that we should really concentrate on the challenges to really get a realistic, I would say, outlook for solid-state systems. Next slide, please. And one of the key requirements for solid-state batteries is, of course, the electrolyte. And there is two, let's say, different functions you need in a battery that have to be fulfilled by an electrolyte. One is the separator function. Now, the separator will be something that is rather thin. It has to be thin in order to have a high energy density of a full cell. So will be rather thin, maybe of the order of 10 or 20, in the range of 10 or 20 microns. And then the conductivity of the separator electrolyte, separator solid electrolyte, does not need to be superior. But if it comes to the catholyte, where you have the cathode material and the solid electrolyte, then is the material that has to be mixed in a composite with a cathode material. What you see here in this SEM picture in the gray circles is in fact a cathode material, and the dark gray phase is a solid electrolyte. In this case, it's a thiophosphate or sulfide electrolyte. And Anja Bielefeld, in one of my PhD students, did a modeling study together with Volkswagen, calculated, in fact, what has the conductivity of a solid electrolyte to have in a realistically thick cathode, let's say 100, 150 micron thickness of a typical cathode with a reasonable loading of active material. How good has the conductivity of the electrolyte to get acceptable C rates? And the answer is, well, and this is something I know I was confirmed by quite a number of colleagues who agree, the conductivity of the catholyte has to be of the order of 10 millisiemens per centimeter, extremely high. And if you look to solid electrolytes, most of these solid electrolytes don't meet that. Polymer electrolytes don't meet that at room temperature. Oxide electrolytes rarely meet that at room temperature. The only solid-state electrolyte system that currently really approaches conductivities of 10 millisiemens and even higher, these are the sulfides and the thiophosphates, and that's the reason why the sulfides and the thiophosphates are in fact those electrolytes that are currently favored for the use, for the major use in solid-state batteries. And one issue is, of course, that you need this high conductivity because you can imagine ceramic materials always have grain boundaries and they have pores, and these grain boundaries and pores increase the tortuosity of your system and decrease the effective conductivity. So to overcome these problems, you need really to have an ultra high conductivity electrolyte. That should not be forgotten, because otherwise you will never have a competitive energy and power density. Okay, next slide, please. And well, this is already what I briefly said. There is these different groups of electrolyte today available. So I think at the left side, I only mention that because for thin film batteries, for micro batteries, there's the LiPon, which is a nitride of lithium phosphate around, which has a terribly low conductivity, but as it is supplied only as a thin film, it works rather well for thin film batteries. For thick film batteries, the polymers do not yet have enough conductivity for room temperature operation, which I think is prohibitive for most of the electric vehicle applications. And only the sulfide electrolytes and maybe even now some halide electrolytes, I think, really go up to 10 millisiemens per centimeter and more. They are rather soft ceramic materials. They can be cold pressed. They can be solution processed. So that's why they are, I would say today, everybody's darling. Well, of course, with the worries that sulfides may be dangerous if they emit hydrogen sulfide. So this is one of the potential drawbacks, which I think seems to be overcome, but also their electrochemical window of stability is rather narrow, and they are easily oxidized and easily reduced. So they have issues with the lithium anode and also with cathode materials, and that means that you have to, of course, take care for the interfaces, which is an important issue. Next slide, please. Okay, that brings me to the key challenges. Next slide. And this is marked here in this little cartoon, which we summarized already a few years ago, but which is still, I would say, quite, this is still actual. And one is, in fact, at the cathode side, the major task is really to get a good cathode composite, a solid state cathode composite that provides good ionic and electronic path without, let's say, compromising the stability. And now the stability, as I said, if you really like to use these thiophosphates or sulfides, you need coatings around active materials, because these sulfide electrolytes already are being oxidized at potentials of, let's say, 2.3, 2.4 volt. That creates an important design rule for the cathode materials, and we can't use the same cathode materials that we use in lithium-ion batteries. Now, and another issue is the chemomechanics. You know, ceramic materials are often brittle. Active materials change their volume upon lithiation and delithiation, and that leads to mechanical strain. And this also chemomechanical effects are something that really have to be solved, because otherwise little cracks can open up and you get impedance increase and your cell doesn't work. Important point is that's why many of the solid state batteries, if you look to literature today, are operated at very high pressures. But in a car, nobody likes to apply a pressure of higher than 1 bar to a battery, because otherwise you need really thick steel plates to keep your battery together, and that of course again compromises all the efforts you have done. So we need to operate solid state batteries at low pressure, and this is really one of the key issues. The lithium metal anode is another issue. I think that's not, well, one may believe, and I think I'm happy to believe that QuantumScape, for example, has solved the problem of the lithium metal anode, but so far there is still issues with porosity, with dendrite growth, with the lithium metal electrode. And if we use at the end more than one solid electrolyte, because we can do that, because we can use a different electrolyte in the cathode than in the separator, we have additional interfaces between two different solid electrolytes and have heteroionic interfaces. So this may open up new issues. Next slide, please. And that brings me to the key tasks. So I think from my perspective, a key issue on the way to a successful solid state battery is still that we have to look for novel and improved solid electrolytes with very high ionic conductivity, more than 10 millisiemens per centimeter in the best case, and superior stability. And it makes no sense to say, okay, I have a good electrolyte with 1 millisiemens per centimeter and superior stability. You need more to really create a proper cathode that can compete. Then we need to be able to process cathode composites with very high density and high effective tortuosity for both ions and electrons, which is very easy in the case of liquid electrolytes, because the liquid electrolyte impregnates everything properly. And here, of course, it is really an issue of solid state processing. The cathode materials need to be optimized in order to get a reasonable chemomechanics of your solid state batteries, because it will have to operate at, well, only 1 bar applied pressure. Otherwise, it will probably not be a practical cell. And that will mean that we also need protective coatings for current, would say, generation cathode active materials, because otherwise they will oxidize the chemically rather unstable solid electrolytes. And if all that is done, we need, of course, to get the reversible high-rate lithium metal anode started. Well, let's hope that QuantumScape has solved this completely. At least, I would say, if you check the scientific literature, I think you may have questions whether this has so far really been able, at least for, let's say, large area electrodes, where you need, of course, then have a very high homogeneous operation of a lithium metal anode. And of course, if all that has been solved, the hardship of processing, upscaling, production has to come, and the competition with costs compared with the lithium-ion battery. Okay, let's go on. Next slide. And that brings me to the end. And let me just summarize then what we do in Germany. I'm pretty sure, and we are quite sure that the future will be hybrid in the sense that we will not see cells that just operate with one solid electrolyte, because there is not the one ideal solid electrolyte. And because this is the case, we created a big research cluster. We call it the cluster of competence. With meanwhile, in the second phase, now more than 150 scientists in more than 20 institutions, where we really address all the subjects from the materials level to the scaling up to components, and then even to the cell, which of course where everything has to come together. So our consortium really combines solid state chemists, theoreticians really dealing with ab initio calculations of lithium anode interfaces, even up to production specialists that know well how to set up not only a pilot line, but also a gigawatt factory at the end. So this is our strategy. We need, I think, expertise from different fields to solve these challenging properties. And I think next slide with that. I'm at the end. I would be happy to receive your questions. Please don't think that my presentation may give a negative or pessimistic outlook. By no means. I have been trained, I think, also within our cluster to be objective and neutral and to really judge development in a neutral way, because if you exaggerate, or let's put it in the other way, with exaggerations, you will at the end never be able to solve problems. So we have to be serious, we have to be honest, and there is still some major challenges to go, and it will take some time, but I'm optimistic that we will at the end see solid-state batteries. Thank you.
Thank you, and you got a question which is sort of touching upon your realistic tone in your presentation. And it is, with so many unsolved challenges, what are the advantages expected from solid-state batteries?
I think this is an excellent question, and of course, something that will try to compete with something that is already existing. You have at least in one of the key performance indicators, you have to be better. Now, what is of course expected, and I think definitely this can be a true advantage of solid-state batteries, can be the temperature range in which you operate. And it's not only that one can hope that higher temperatures can be, let's say, survive easier. It's also that the operation at low temperatures may be better. Toyota has shown quite nice results on low temperature operation, because while a liquid electrolyte can freeze out and transport quickly gets slower, a solid electrolyte is already frozen. And the activation energy of the excellent electrolytes is rather low. So the solid electrolytes don't lose that much conductivity if you go to lower temperatures. So temperature range is one example. And with that, along with that comes, of course, safety. That may be an advantage, but of course, before you can claim that a cell is more safer than another, you need, of course, to demonstrate large-scale safety tests, which I have not seen yet. And then, of course, the hope is that one can get, of course, if the lithium metal electrode can be operated in a solid-state battery, that we really still can gain some specific energy and also some specific power if that can be made, as I said, reversible and high rate. So I think there is hope for major advances, but of course they have to be proven first. So don't take it as given that all that will be there. So that's why it's all a big bet, and we have to work very hard to realize that.
Thank you. It's actually dropping in a lot of questions for you.
Okay.
And some of them I think we also should save for
yeah, of course.
Panel discussion.
I will be happy to save them for the panel.
Yeah, it's actually very good questions for the panel something, but I think this one may be more technical. How can external heating of the cell in EVs help to solve the temperature issues of choice of materials? Yeah.
Well, I think I have a simple answer to that, which well, I may be wrong, but I had discussions with OEMs and they told me, well, never ever will a battery in a car be heated. Quite simple. Either it operates at room temperature or it will not operate, or it will not be used. I think for buses, as I said, for vehicles which have very regular, let's say, very regular driving schedules, more or less around the clock, you can do that, and that's reasonable. But for a car that may stand just for 2 weeks out there, it seems not to be reasonable to have a heated battery. So this is from the OEM's take, but I think I agree with that.
Thank you so much, Jürgen. And several of the other questions, some of them are overlapping even. I think
Okay.
we now save for the panel. So I will now invite the panel, the first panel, to the stage. And we have the title, How to Accelerate the Research to Enable Solid-State Batteries. And we have 3 panelists here. And if Jürgen could also stay, of course, we would think that would be very fantastic. And it's Mauro Pasta, who is Associate Professor at the University of Oxford, belonging to the Faraday Initiative. I think you will soon present yourself a little bit more. It's Fanny Bardet, Program Manager at the RTO IMEC in Belgium, Corsin Battaglia from EMPA in Switzerland, also an RTO. And if you very quickly, each of you, could just give a few sentences of what is your specific take with solid-state batteries. What are you focusing on? And I think I start with Mauro, because you're first to the left on my picture here.
Great. Thank you very much for the invitation, Christina. Glad to be on the panel. So I'm Associate Professor at Oxford, and I'm leading the SOLVA project, that stands for Solid-State Batteries project within the Faraday Institution. So what we mostly focus on, I guess, in general vision is very similar to what Jürgen has just presented, mostly inorganic, ceramic, solid electrolytes, mostly focusing on lithium metal, with the idea that we're not there yet, fully agree with Jürgen, but we want to focus on a chemistry that is superior to lithium-ion batteries, at least in one of the metrics, ideally in all the metrics, if it's possible. And as of today, the only chemistry that will get you there, it would be an inorganic ceramic, agree on the sulfides with the higher conductivity, and probably metallic lithium negative electrode. So hopefully that gives you like a 30-second summary of what we do.
Thank you so much. It did. Fanny Bardet.
Good afternoon, everybody. Thank you for inviting me in this panel discussion. I'm glad to be here. So I'm Fanny Bardet, Program Manager at Solid-State Battery at IMEC since 3 years. Before that, I was at Toyota for a few years working on next generation battery for automotive. At IMEC, we are focusing on developing solid-state battery based on different component materials. But I think a strong point of IMEC is to develop interface control because of the background on microelectronics. IMEC knows very well how to control interface, and that's the key point we use. In addition to that, I'm also project coordinator of a European project in LCBAT1, which is called Solidify project, where we have 14 partners. IMEC is coordinator, 14 partners in Europe. I see here Corsin is also part of this consortium, where we try to increase and demonstrate solid-state battery cell at a higher TRL level, TRL 5, to go from 3 to 5 using solid-state electrolyte and different expertise from the different people from the consortium. So I think in general, I agree also with Jürgen Janek that indeed we have to focus in general on solid-state battery in trying to make these cells, solid-state battery cells, working at without too high pressure. I mean, without applying too much pressure around the cell, because then you lose all the advantage you have by trying to increase the performance at cell level, watt-hour per liter, and also to work at a decent temperature for, if you think of passenger cars, you have to be able indeed to work at low temperature, room temperature. Well, I think that's my introduction. Thank you.
Thank you so much. Corsin.
Hello and good afternoon also from my side. I'm head of laboratory at EMPA, the Swiss Fellow Laboratories for Material Science and Technology. And I'm heading a laboratory there with about 30 people, of which about a third are working on solid-state batteries. We've been working on solid-state batteries now for more than 6 years. And I think the topic has evolved from, developing materials with higher conductivity to more and more also integrating them into cells solving interface issues. And I think the big challenge here is also that we know now several electrolyte classes. They all have their benefits, but also their disadvantages. In my lab, we work on ceramic electrolytes, ionic liquid derived polymer electrolytes, and also hydroborate electrolytes. And they all have their specificities. They are all fulfilling certain criteria, but maybe not all the criteria at the moment. So we're working basically to also combining different electrolyte systems to get these cells to work. And I think also with the vision and somehow the hope of being able to get lithium metal, or for example also sodium metal anodes to work, because then you really have that promise of increasing the energy density quite significantly compared to current lithium-ion battery technology.
Thank you so much for these presentations. We're linking really well into Jürgen's presentation. And Jürgen started by saying we have some way to go. And the chat is now flooding with the discussion. When do you think they really will come out on the market? From a science point of view, a scientist trying to be neutral and not promise too much, what do you think is realistic? I think I should start with Mauro again, because I know that you have some pressure on you in the UK to actually go towards upscaling. And how is that going?
I think we all do in a way. We need to find a good balance between being scientists and tackling the fundamental problems that I absolutely agree with Jürgen are still there. And you're not going to solve these problems by simply manufacturing, trial and error, and hopefully we're going to get there at some point. We need to focus on the key fundamental scientific challenges. I agree with Jürgen, 4 main areas: lithium metal solid electrolyte interface. We still have quite low critical current densities to this date in the ceramic solid electrolytes. We've done a lot of progress in understanding what's going on and the mechanism of dendrite formation, but still progress needs to be done on that front. Cathode, key. We need to decrease the pressure that are required to operate. Jürgen mentioned 1 bar. Maybe we could do with a little more than 1 bar, but definitely not the 10th of megapascal that are required right now. That's a given. On the solid electrolyte side, I think we have few options on the solid electrolyte, on the sulfide space. I don't think anyone is fully happy with any of them. Hybrid is one way to go. I think maybe there is still some room for electrolyte development, in particular bringing in these new computational or mixed computational experimental approaches to material discovery, hopefully find better solution there, and then focus on the science of processing. Because there is science in processing, on the contrary of what a lot of people think. Typical example, densification of solid electrolytes. It's actually very interesting science there. So from that point, it's very difficult for me to make a prediction. I think it's good to have a little bit of pressure of moving out of a lab and turning into prototyping. And I also think that it's good and healthy to have prototyping activities in parallel to the fundamental scientific work, because I think the solution to this problem will be probably found at the intersection between manufacturing with dedicated facilities to prototyping and manufacturing, and very good and solid fundamental science to support such facilities. So as you see, I talked for a couple of minutes. I didn't give you a date because I don't feel comfortable providing a date on where to become commercial. Because, challenges, we made a lot of progress in the past, I would say 5 years, and I think we'll make even more in the next 5 years. From there to scaling up at the levels that will be required to become commercial, that's a completely different game. Definitely is not going to happen in the next 2 or 3 years, like several players are saying these days. I believe it's more on the 10-year time scale. Yes, that would be my thinking on this.
Thank you. And what do you say, Fanny? You come from Toyota, and Toyota said it would be on the market 2020. Now you are on IMEC, so I will not blame you for this. But what is your...
Yeah, thank you. So basically, can you hear me? Yes? Okay. So I think, yeah, we have to be realistic that there is a big gap between between what we do in the lab, in research institute, academia, what is done in industry. I think there is a long way between, even if you have a prototype, I would say if the cell is 3 ampere hour, 5 ampere hour, and the time it will come in a car where it's fully safety standards are passed, quality standards are passed, and so on and so forth. There is a huge amount of time and effort to be done. Nevertheless, I think if there is a possibility to collaborate strongly immediately with the, let's say, the car industry, the end user, that they will be involved much sooner to help the researcher and the startup or the small enterprise to develop the right prototype. I think we can really close that gap and make it shorter than it is today. So I would be in favor to say like more, okay, 10 years, but if we change the way of working and the way interaction between industry and research, I would call it research, is done, we can go faster. But I think still indeed, as I say, the prototype at higher level is needed to have the requirement from industry checked before the cell is, let's say, chosen to be implemented into a vehicle. So that takes time, and we can, I believe, I'm optimistic that we can shorten that time, but we should also not expect it's in 3 years. So I would be maybe a bit more positive or shorten that to 7-8 years to see solid state battery in vehicles. That would be my answer.
Corsin, what can you add to these two comprehensive responses?
Yeah, so I fully agree with Mauro and also with Fanny. I think, I mean, there are open fundamental issues on the science that science has to address and can address. Specifically, your question on when batteries will come on the market. You know, when I brief my PhD students, when they go to have interviews with journalists, I tell them, the only thing I tell them in advance, you know, don't give them a prediction, so I won't make one either at this point. But I think an important point is also that we really think about how can this be adopted? How can solid state battery manufacturing be adopted by, you know, this very huge production capacity we are currently putting in place into Europe? And for example, in the Solidify project, you know, the name is Solidify, so we can actually solidify that electrolyte out of solution. And for example, a process where we could infiltrate it into a prefabricated electrode, for example, that would maintain a certain amount of steps in the production the same, where we only have to adapt a few things. I think thinking about plug-in solution or drop-in replacement in the current production scale would really be helpful to accelerate also the introduction of solid-state batteries at scale.
You hear this, Jürgen, you get some support in your your presentations. So what would you then say? Do you believe in 10 years, or do we expect it in 20 years? Or
well, it really, I made the experience, and I discussed with a lot of people that it really depends so much on whom you ask. Now, if you ask a production specialist who is currently setting up a gigawatt factory for lithium-ion batteries, he will tell you that it will take quite a while, because so much has to be done to really be able to set up a gigafactory. So I think he or she will then surely say, well, it will take at least 10 years. If you ask, of course, the closer the people are to research, the more optimistic, of course, they will be about progress as such. But then, in fact, the gap between, I think, research, between lab cells, pilot lines, and upscaling has to be overcome. And a lot of, I would say, cost issues also come up. So I would say, as I said, I'm optimistic that we will see solid-state batteries. It will be, I can't really tell you on what scale we will see them. I hope that we will see successful competitive solid-state batteries that can bring further progress relative to lithium-ion batteries. But I think it will take time. But now, that at the same time saying this means that we still have time to, of course, I would say, to build a proper strategy, how to really bring that up properly. So I think this is a good message, because if I would say, okay, in 2 years it is there, well, then I think Europe would have no chance to do anything with that. But as there is still some time, I think we have a chance to really compete and to be part in the development.
Thank you. That brings me actually into something we discussed yesterday in the opening panel. This that we have a window now of opportunity to really, because we are joining forces in Europe, we put resources in place, we put gigafactories, hopefully, on stage in Europe. And I think Fanny very wisely said we need to change the way to work. And some worries I've had myself is that industry and research, the gap between industry and research has increased it since I started with lithium-ion batteries in the mid-90s. So from that perspective, how do you think we should change the way we work to really accelerate how we can have a better prognostic tool to say, now we can at least trust that these batteries are safe enough, they are green enough for us to really have as a product, whatever market it will be. And I think this time, I start with you, Fanny, this time, because you said it so wisely. Change the way how to work.
So yeah, I think if you look at Europe today, I think there is a lot of collaborative research, which is very good, and it's very well supported via the different initiatives where large consortium can be built with several partners with different expertise from all countries in Europe, and bring work together for 4 years to develop certain prototypes. I think that's very good. Nevertheless, I want to say that maybe we can do better. For example, I'm thinking that there should be maybe more place where there is large dry room where different group could come to test new equipment, test new manufacturing lines. That could be very interesting. I know there is a Lithium Planet activity going on, but maybe we should put even more emphasis on that type of supported activity from Europe. A second thing I think is very important is to think in research institute, yeah, you are doing a lot on new material, fundamental issues, development. But I think at some point you have to, probably the best way to accelerate the research is to, once you have a good enough, let's say, set of components, to spin off part of this research activity into a startup or a spin-off in order to accelerate and close the gap between TRL 3 to maybe 8, to be able to make larger prototype, to really focus on specific components you think are the most promising at that moment. And from there, you can attract a bit following the US way of working, I would say, because you see there is a lot of startups, but maybe on a European style, maybe being also more honest in the way we approach, the way we would like to report the result and let's say test the different cell performance. So I think that's maybe something I would change in the way today we work in Europe, put more emphasis on smaller consortium with 2-3 partners to specifically focus and accelerate one specific development to see, okay, can we make it a product or not? And that we can answer that question within a shorter period of time. That would be my recommendation then.
Yeah, well, thank you. Have you any thoughts about this, Corsin?
Yes, I think we are currently extremely fortunate because there's really an intrinsic interest also from companies in solid-state batteries. So as Fanny pointed out, I think the funding is there, the interest is there, the motivation is there, and we are actually working together with a startup company in trying to bring some of our chemistries closer to commercialization. I think what is challenging sometimes from our side when we are in these new chemistries, we have to solve a lot of problems. A lot of issues have to be addressed, and the expectations currently from the companies also, they are huge, right? And I think this is also something where we have to meet each other somewhere midway. It's okay to be ambitious, but sometimes I think if the expectations are too high, Jürgen pointed out it's a hype at the moment. You know, it comes with a hype, this high expectation. You can also see the stock market, what kind of effect this has on batteries, but I think we have to really address the issues and work closely together, and maybe putting a bit the hype aside at the moment.
Thank you so much. Maro.
I agree. I think the fundamental problem very often is the timescales we operate on. Research and development, you can make a plan on development. Very often you cannot really make a plan or a good time plan or fundamental scientific issues. The answer sometimes could be that an issue cannot be solved, and you should be comfortable with that. So it's the whole idea of bringing together the fundamental research and the expertise that are fundamental issues we have in academia and development that should, in my mind, be done in collaboration or fully led by companies. I fully agree with you also, though, Christina, that in the past, I would say 5 to 10 years, the gap between fundamental research in academia and industry has widened. Solid state is probably one of the few technologies that is closing this gap, because we're appreciating on both fronts the challenges, and then we need each other in a way. It's not enough to focus on fundamental research. You need someone that can help you and support you on prototyping, and vice versa. You cannot only push through with engineering because there are some fundamental issues that need to be addressed. So in that sense, I'm more hopeful on the solid state side that this gap will be closed. And I think, that's the only way where we can make progress and accelerate that progress.
Yeah, thank you. I can't help asking Jürgen this question. What's always discussed in, at least in my country, Sweden, that is consortia are perfect when they are about 10 people. When you make really big groups, how are you efficient? And you are now kickoffing with a very big group. How do you build that in an efficient way to really have the research and the link to innovation in a smart way? How is your sort of experience of building big?
Yeah, that's a good question. And sometimes you think it's just a group of sheep, right, which you are trying to bring in the same direction. So I think in our case, our cluster is divided up into 7 consortia, sub-consortia. We call them platforms. So we have 3 materials platform, 1 hybridization platform, 2 cross-sectional platforms, and 1 production platform. And in these platforms that are all more or less independently funded, but are under the umbrella of the cluster, the cluster coordinator, so me, has an own project with own scientists. Well, the only task of this coordination project is really to coordinate and to steer and to discuss with the people and try to coordinate their work. So I think what you need is really smaller scale projects. So each of these projects, let's say, has maybe between 5 and 8 PIs. And these work very well because they can really operate quickly, like a little sailing ship. And they are fast. And then I think you need an overarching project where there is really also scientists who have nothing else to do than really to analyze the results and to bring people together, where their task really is, well, to steer. And that seems to work relatively well, I would say, so far. And then we have the industrial management board that is observing that and is discussing with that, but they don't have real, true, let's say, so they cannot kill us, but they can, well, strongly recommend things. And that seems to work relatively well, I would say. But nevertheless, even there, I think you see often these issues. So I think, let me be a bit critical. And I think if you ask what is really necessary. Now, if we know that, for example, for a good solid electrolyte in the cathode material to get a competitive battery, you need, let's say, 10 millisiemens per centimeter. Why do people then do research on electrolytes by claiming improving a solid state battery if the electrolyte is 2 orders of magnitude worse and doesn't show any, I would say, indication of becoming better? So I think this is something, if you really aim for, let's say, this kind of applied research, I think you need really also to streamline your research. I think if you like to do fundamental research, understanding mobility in electrolytes, that's pretty fine. There's, of course, lots of need for this research, but then you should not tell that you improve the solid-state battery. So I think this is something you need honesty about, real, true, let's say, key performance indicator. And I love to be a fundamental scientist, but I have learned also that in order to really achieve a direction, people have to accept that they also have to do directed research. And this is, I think, the challenge.
Thank you so much. I tend to agree with what you're saying. And it's good that you have a model with sailing ships to make an armada.
Yes, right, exactly.
Yeah. We have a few minutes left before we let the next panel come in. So I will just now bring in some of the questions from the chat. And I can see that some of them are really focusing on eco-design, recycling, etc. And of course, one can say, is it meaningful to have these perspectives from the start, or is that something you move to later when you have your systems really functioning? What is your take on how we should work on really ensuring sustainability when it comes to solid-state batteries? I'll let Korsin start this time.
Yes, I think, I mean, there's a new battery regulation now, you know, which has been put in place. And of course, I mean, the first thing is we don't want to work necessarily with super hazardous substances, critical substances. Think about carbon footprint. But I think very specific to the solid state battery is maybe Article 11, you know, removability, replaceability in terms of the design to disassemble the cell, you know, that we built that in already. And I think if we are thinking in terms of traditional lithium-ion batteries, it's already relatively difficult to separate the components, but it's still feasible, right? So you don't have to necessarily just burn the whole battery to recover the materials, and that's for the carbon footprint, that's an important aspect. Now, on the solid-state battery, you are making this kind of big cake of solid material, and you need to be able to disassemble it, right? So I think there, I mean, big if it's odds, definitely. One option is, for example, we are developing an electrolyte which is water-soluble, solid electrolyte that you can basically at the end of life put this battery into an aqueous environment, dissolve this electrolyte, which in our case is a salt, and we could actually even recover that salt just by, you know, drying it out of the water again at the end. So I think indeed, I think specifically on this design to disassemble solid-state batteries should consider that in the future even more strongly.
Thank you. How do you take that into account, Maro, when you have your big UK project?
I mean, we think about this, right, as much as we can. And it's something that in academic community, I think we've been thinking about for a while. You know, we've been known that cobalt was a problem. We know that some processing and recycling will become more and more relevant. We have a chance now, considering that we're designing a battery from scratch in a way, to include recycling and include raw cost and material in the designing process. It could be a further down selection tool. Of course, he mentioned the recycling solid electrolyte, very good point. There's always the temptation, I would say, on the cathode side to add a little more cobalt in our cathode in solid electrolytes for the reasoning we mentioned earlier, right? Volume expansion. When you cycle your solid state batteries with lithium cobalt oxide or cobalt rich materials, you know, they all look nice and work very, very well, right? But we do consider this, and it's a big opportunity that we have to design solid state batteries that are mindful of recycling from the ground up.
Thank you. How do you feel, Fanny? Would you have a comment on this as well?
I think I want to say I've been working as task force leader for sustainability, the new position paper, and I think it's important, and it's already happening in a European project, that the life cycle assessment of the new battery technology, for example, solid state, is now one part of the deliverables. Like there should be from the beginning an analysis of what material are used, in which quantity, what are the process used, Is it high temperature process? Is it water-based process? Does it use solvent? All this has to be, let's say, at least analyzed, at least from a theoretical or modeling point of view, to have an assessment while you develop some prototype, what would be the, let's say, impact, so the life cycle assessment of such kind of new type of battery. So I think this is an improvement. Most of the projects now have this kind of assessment including their deliverables, and it makes the whole community, the academia, the R&D, all the partners along the value chain responsible, and also force them all to think about it. So I think it's a very important aspect when we design the battery of the future, the solid-state battery, to have that in mind. And I think it's already start to happen. I can only hope that it will continue even further in the future, that it's just a reflex at the end, right?
Thank you very much. I think this is a good end of our session. I would like to thank you all to take part in this panel discussion, and I hope you stay on and see how our industry representatives react to the discussion we've had. So I would like now to call for the next panel here. So you see now we have 4 new persons coming in to the discussion, and it's Noshin Omar, founder and CEO of ABBE, called Avesta, which is a city in Sweden. I like that very much. And then we have Dr. Alessandro Chiuvato from Solvay. We have Marc Deschamps from Blue Solutions, and Xiaoxi He from ID2021. It's really great that you are here, and I know that Xiaoxi has to leave quite soon. So I think with you, like last time, that you briefly present yourself and what your sort of role is when it comes to solid-state batteries. So please, Xiaoxi, please.
Yeah. Can you hear me well? Hi, everybody. Good afternoon. And it's really my great pleasure to be here. I'm the research director at ID2021. And so basically, our company focuses on technology and market research. So we don't really do the exact experiments, but we really focus on the different technologies and make assessment benchmarking about their capability. And also we look at the potential market development as well as the different activities of global players. So we don't really just focus on a local market, but the global. So because different regions, they really show different status, development, and even the technology focus could have a kind of tendency. So it's really interesting. I'm really looking forward to the panel discussion. Thank you so much.
Thank you. I ask you to mute now, Xiaoxi, but I come back to you. It's some echo, you see. So it's thank you. And then I move over to Marc Deschamps.
Thank you, Christina. I'm very happy to be there this afternoon. So I'm electrochemist and I'm test manager for Blue Solution. And at Blue Solution, we are already producing lithium metal polymer batteries, so it's a solid-state battery. We are making our own electrodes on making the cell, the module, and the pack. So it's a big battery, so dedicated for buses or stationary application today, but we are working hard to have a solution to reach EV market with the room temperature. So thank you.
Thank you so much. Alessandro?
Yes, hello everyone. My name is Alessandro Chiuvato. I am head of program management at Solvay, part of the battery materials platform. In our entity, we have several programs to develop new materials for current and future generation of batteries. And among these programs, one of the most exciting is the one dedicated to solid-state batteries. we are both working at developing inorganic solid electrolytes, but also on the binders that will be used as binder in all solid-state batteries. So I'm very happy to be here.
Thank you. And finally, Noshin Omar, please.
Yes, good afternoon to everyone. Noshin Omar, CEO of EB, Avesta Battery Energy Engineering, located in Belgium. I am used actually to use my academic background over 14 years and to combine that with a realistic approach which is coming from the industry. We at EB are developing solid-state technology based on sulfides, which is the electrolyte, and lithium metal, which is the counterpart. And this is now under assessment by independent third party, which is the Politecnico di Torino, and we hope by beginning next year to share the results to the full community, and I'm looking forward to this discussion.
I'm actually going to start by asking you if you have any specific comments and reactions on the previous discussion, because it was a lot of many in the chat asked for this question when and this confusion about all the challenges we have and how we should solve them, and when we have something on the market. What is your perspective on what you heard before? Can I start with Xiaoqi again, please, with your market perspective? What is your own take on this?
Yeah, sure. I think many people talk a lot about the commercial license time. So actually, when we talk about solid-state battery, there is a gap between like academia and also the market, the public, how they could interpret a solid state. Because we know there are different technologies. Some are based on inorganic ceramics, others based on solid polymers. There are also options of semi-solid. But for the end users and also OEMs, they don't really care about what technology you are using. What they care is about the final value propositions and performances. And that's why, like in the market, lots of people, they call the technologies as solid state, but in reality, or strictly speaking, they are not solid state. But we use the same terminology to talk about different things. So that's why different people may have different opinion about the commercialization time and also like manufacturing challenges, etc. So for us, we have seen lots of companies who have their manufacturing plan. So for instance, after 2025, but in reality, like some of the technologies are really close to current lithium-ion battery technologies. So they have some kind of improvement, but others, they have like a fundamental change. So that will lead to lots of research difficulties, like the optimization, lots of mechanism study, etc. I would say when we talk about the commercialization, we need to think which technologies we are talking about, and because that will lead to different supply chain, the manufacturing challenges, and even like when you come to the pack design, that will also lead to lots of difference compared with the conventionally lithium-ion batteries. So that's just something I want to emphasize.
Thank you so much. There is some echo when we are talking, so when you're not speaking, please mute your microphone, because it's very disturbing for the ones listening. It became better, I hope. Well, Mark, you are in production, so for you this question must be a bit strange. What do you think about this?
Sorry, I can't catch your question with echo. So can you?
I was asking what your can everyone mute the microphones, please? Thank you.
Okay.
I was asking if you are already in production. This question about when it's coming must be very strange for you. So yes. What is your reaction to this?
So we are already in production at a, I would say, big level of capacity, not megawatt, but not so far. So it's a strange question, but I think Blue Solution is not well known on the market because we have a warm battery. So it's of course a big disadvantage for EV, but for bigger application, I think it's not a so big problem because in many cases you have to cool down the lithium-ion battery. In our case, you just have to warm, and probably it's simpler to warm than to cool. And one point I want to address is the processability and manufacturing for solid state is probably a big subject to solve for the future. So it's very interesting to work on the process to develop a solid state battery.
Thank you. Noshin.
From our perspective as EBA, we believe that solid state is coming. But the approach, how it's now tackled, is not going to be straightforward approach. First of all, the challenges actually are not only just fundamental. There is significant need for applied research. There is extension, increase of knowledge needed in regarding production, processing, even equipment. If we look to the supply chain here in Europe, even many of the equipment suppliers, they don't know even what is solid state. What are the right equipment for that? How to scale that up? That is something completely missing and on top. So we have to look to the full picture and not just to express that in small pieces. Secondly, from a market introduction, we believe solid state will not make it directly the big introduction. The big introduction will be in very specific segmentations of vehicles, which are supercars, hypercars, race cars, where the cost is not a big issue. On it all, the scale will be increased. And then we go to the long range vehicles, and then afterwards to another segmentations. But we have also to be clear and to give the right messages to the industry and to the full world about that. Solid state will also not be the solution for the full applications. Solid state will not be a solution for city cars. Solid state will not be a solution for bikes or scooters, whatever. And these messages should be also given in a very proper way and a very clear message to everyone. And because many industries still believe that solid state is going to be a competitive solution to lithium ions, and our answer to that is no. Solid state is just going to be complementary, something needed in addition to lithium ion for some diverse of applications.
Thank you, Noshin. So, Alessandro, what is your take on this? Do you agree with Noshin?
Well, yeah, I think that all my colleagues have said something of value. I think, first of all, Xiaoxi clarified one point on solid state. We put different type of technologies, and not all of them have the same properties and the same time to market. So we see the Blue Solution is already producing since several years, which are to a certain extent state, but I think that when we talk about solid state, we intend more the final evolution, which will be inorganic electrolyte, all solid state batteries. I think that I share some of what Noshin has said in terms of time to market and how the technology will enter the market. It will not enter as a mainstream technology for EVs. It will enter in niche applications, which is a quite standard way where new technologies are actually put in the market in e-cars, so in Formula One cars and so on and so forth. I'm a little bit more optimistic in terms of the timing because Solvay is actually working together in one of the challenges that were mentioned by Jürgen in the industrialization, in the scale up. And we know that this is a difficult point, of course, but we have started with a prototyping unit, and we believe that we might have some real industrial production in the second part of this decade, meaning 2026, probably 2027, already some quite significant amount. And we are working very closely with the other parts of the industry, because as it was said before, there is not one company that can work all alone. We really need to work very closely in consortia to be able to have all the competencies around the table. So I'm a little bit more optimistic in terms of timing.
Thank you so much. I think this how we should work together is very interesting question. We had it with in the earlier panel where we said, can we change the way they work? And then it was pointed out that working directly between industry and academia in a much more efficient way than we are doing now is one way forward. How do you think we should accelerate the way we work to actually enable solid state batteries to enter the market? I think I start this time with Mark, because you have some experience already.
Yes, we have some experience of collaboration with team, so it's a good point for us to have an exchange with scientists in Europe, in France, and sometimes in the world, and it's very interesting to have a new point of view on how to optimize a solid state battery. So it's very important for us to have a look on what it is. What is the main subject, or what is the main results they obtain on the different subjects we are interested in. And concerning the subject, we are very aware it's a key point. It's on the lithium side. We believe we have to improve our knowledge on the lithium metal deposition and how it's cycling. And the second point is what is the effect of the pressure on this kind of cycling.
Thank you. So, Alessandro, you work for a big company with, and you are part of many EU projects, of course, already.
Yes.
Is there anything specific you think in how we should work that should change? Are there any competences missing? What are you looking at for that you would need to accelerate this transition?
Yeah, it's a good question. Sorry, one thing first, Noshin, if you can please mute yourself. I think that the echo comes from you. Thank you. Yes, indeed. I think that first of all, one big step has already been done. As you said, the industry and the academy have started working together. This has also been facilitated by initiatives like the IPCEI dossier. That allowed to fund the industry to accelerate, and in a way that pushed for collaboration, really for working around the table with all the competencies. I think that this is something that is fairly new and still perfectible. To me, is not a matter of missing competencies, but really defining a new way of working, which is to a certain extent more open. And God knows how we have been trained in being very secretive with all what we do. And I experience personally that this is sometimes a break to the acceleration that we are expecting on the innovation. So we work together, but I think that we need to work together in a more open way to foster this acceleration. And of course, I think that we need to look into more interactions with the academy, because I totally share what Mauro was saying in the previous panel. there is a little bit of disconnect between fundamental science and how things work and how the industry is proceeding.
Thank you. And Noshin, setting up a new company, you must have faced this with having competences and thought a lot about how to work. So what is your message?
Now, from EB's side, we believe, and to such extent, I agree with Alexandro, the collaboration is needed, but we need also at European level quite clear focus. We have in Europe some dedicated competences, quite a lot to such extent on the electrolytes, on the cathodes. But if we look to the lithium metal part, let's be very clear, the competences in existing right now in Europe are quite pretty poor. And so we need their very dedicated focus points between the academia and the industry. But nevertheless, this full process should be coordinated by the industry. Industry should define the goals and the objectives, which actually where academia and the applied research should to support, and not vice versa. And that is actually at this moment, if we look to European research programs, we see that actually the same topics are popping up every year without a very clear focus. So we start working on fundamental things without having a clear objective, what is going to be the final product. And then we come to the conclusion that it cannot be produced. So there and closer collaboration and alignment between industry and academia is needed in order to achieve the final goals in a faster way. And let's say from our perspective, this is quite a weak point at this moment.
Okay. That I can't help asking this question as a follow-up question for you then. We have now been organized in a new battery partnership, which is mainly industry-led. Will that lead to any changes, you think? Or is it the academy so well rooted in their national structures that it takes time to transform this?
To me, Maria Cristina?
It's a question to you, a follow-up question to you.
To such extent, yes, correct. But I believe that alignment still can be done better with a very clear strategic roadmaps coming out from the industry, particularly from the car manufacturers, which are going to be finally using the products. And that's not critical, but at least something which I can say that is still missing in the overall picture. And in another continents, like in Asia, in US, the process is happening differently. The leadings are the automotive industry, and the supportings are the academia and the research centers. And I think that's something similar we need that here much more in Europe.
So how would you then balance this, that we need long-term research, which is visionary and maybe go outside the box, and this useful research? I think we could have both, I guess. Do you see anything from your experience, Xiaoqi, from the market perspective, how this interplay between research ideas and industry and the coupling? Have you any ideas about this that you see?
Right. I try to answer that from a different perspective. So typically, it could be a case that for the research group or companies, they have a product or technology and they are looking for solution. There is another aspect is from the demand. So for instance, the automotive OEMs, they could initiate or they have a dominant position in the no matter research or the whole project. So they have a very clear target and they are looking for a proper target or technology to fulfill their requirement. So what is tricky is to find the meeting point. But in reality, we actually see the efforts from both sides. So as Noshin mentioned, like in Asia and in the US, there are lots of created by automotive OEMs. So they invested in some startups, and also they have some co-development. and also build a joint venture. I think this is a really interesting approach because the batteries will have a final targeted application, and from this process, they have a really clear guide, like how they can become closer to that point. But the other part is that when you have a technology and trying to look for solutions, for those companies, what I saw is they have lots of efforts and trials, maybe not just limited to electric vehicle applications, but there's lots of other niche applications. There are lots of efforts. So those are just some different routes people tried.
Many good examples of what we could learn from, I guess. Alessandro, how are you working at Solvay to really convince the scientists to do what is useful for you?
Yeah, I think that is obviously a good question, but we are working very closely with this is a first point. We need to define very clearly at the beginning what is the purpose of what we intend to do, and then we try to back engineer what are the problems that we need to solve and what are the aspects that we need to move forward to be able to succeed. So I think that it is very important that we try to clarify since the beginning what we would like to be the end game, and to what are the different tasks that we need to achieve in order to succeed. And to do that, we have several steps, including very early stage prototyping, but also very important collaboration that we want to establish with the institutes and the academies that can bring the competencies that we do not have.
Thank you. Mark, how are you working with the scientists more practically?
It's an interesting question, a difficult question, because there are different levels for research. You have to solve some problem very urgently and for production team. So you have to choose what are your priority, if it is short-term or long-term research. So generally, it's a short-term research you have to do, and as we have a limited power for research, we can only work on few subjects at Blue Solution, but we are trying to choose the best one, and we are collaborating on that subject. Yes.
I think it's an interesting question how you make an ecosystem. You have the big companies with muscles. They have their own scientists that can pick up research and pick up interesting young people and so on. You have smaller companies, we find it more difficult to find the right connections. So how you make this melting point in a quite heterogeneous structure like the European landscape is not trivial. We have a lot to learn, I think, from both US and Asia on this. Like Xia is saying, I think that was very wise. I think we now should try at least to put in some of the audience. We have a little bit of a Q&A session before we end. And there, it started to become a discussion in the chat, I could see, about safety. What is the safety characteristics you think of your Blue Solution concept? How safe is it if you compare to lithium-ion batteries?
I think it's quite safe battery because there is no organic solvent inside. We have polymer, but it's a safe polymer, and we are safe until the melting of the lithium. So it's a quite high temperature. It's 180 degrees. There is no exothermic reaction inside, the opposite of SCI of graphite when it's decomposed at high temperature. So we believe we have a safer battery, but it's always difficult to say we are safer than the other. So it's just a question of test.
But your battery is operating at slightly elevated temperature.
Yes, but we have more than 100 degree before the melting of lithium. So it's
yeah, but when you use the battery, is it 40, 60?
It's between 50 and 80, yes.
Between 50 and 80. So if you try to go for room temperature, Alessandro, why is Solvay interested in working on both polymers and inorganic? What do you think will be the first step?
Yeah,
how safe will it be?
Exactly. First of all, Solvay, as I mentioned, is quite agnostic in terms of technology of the battery. We are trying to develop materials that enable different type of batteries. So we are both working on the polymer type and on the inorganic solid state. On paper, we believe that the inorganic solid state will present ultimately some advantage, in particular, of course, if all the issues are solved. In particular, on some type of structure that can be built, some design, and on the thermal management that is today one of the parts that add cost when the battery is integrated into a car. So as I said, we put today more efforts on the inorganic solid state, because when we try to make all the expected needs in a radar, at least on paper, this is what ticks most of the boxes. So that's a little bit of a bet that we're doing. Nevertheless, as I said, we are also providing materials to companies that are developing other type of batteries, because they might be easier to put into the market, easier to drop in existing facilities, while probably the inorganic solid state will require really a new type of facilities.
Thank you. And Noshin, you are aiming for large-scale storage and trying to have a factory and build on. How would you handle the safety issues?
Now, first of all, safety, we have to look at from an overall system approach, a battery pack level. And when we have a battery pack for an electric vehicle, there's a lot of safety measures that should be independent if you have lithium ion or solid state. Those solutions should to be guaranteed. Nevertheless, I think we have also to agree, and there is some misunderstanding in the academia, that solid state is fully safe. Fully safety doesn't exist. In particular, if we look to the sulfide-based solid state electrolytes, there's a lot of safety issues regarding handling of the sulfide with all the H2S gas formations, etc., and even the integration into the battery pack. So we have to look at from the overall system approach, and also what types of solutions that should to be integrated in, also in order to guarantee the safety in a proper way. So, I mean, everything is safe so far if you use it in the right way. If you start exaggerating, even solid state could be unsafe to such extent. And that's something which I agree with Mark. We have to look at in a perspective and the area which should to be used in a proper way.
Thank you. I have a final question from the chat, which is a bit sharp to you from industry. This is very interesting, but I have a complementary view. Industry is interested as a participant in EU consortium because of the funding, and not because of they are really interested in the development of the technology, especially at low TRL. Do you agree with this? Are you not interested in low TRL research? What do you say, Xiaoju? Do you see from your market analysis a lack of understanding the need for low TRL research?
Yeah, if we don't if we don't just focus on the European market, but look at globally, I would say this phenomenon does exist, especially because different countries, they have their special fund, not just for academia, but also for the industry. There are also some investment, and the solid-state battery is a really interesting concept from many different aspects. I would say this is a phenomenon does exist, but I wouldn't say like it's a really wide situation or problem. That really depends on like other people. They may have like different perception and view.
Thank you so much. Unfortunately, our time is out because we had continued to discuss this a long time. And you from industry, you didn't have to answer this sharp question, but I thank you all for participating in this panel discussions. Thank you so much.
Thank you.
Thank you.
And now we have coffee and networking. Don't forget to network, and don't forget the Battery Young Research Award, 4 o'clock.
Perfect. Thank you.
Thank you. Bye-bye.
Thank you. Bye.